What we're going to look at now is Newton's universal gravitation. This is something that's going to help us a lot because our usual way of calculating gravity, right? We had force of gravity equals mass times the acceleration of gravity. Useful, but really only on the surface of a planet or anything like that. It's not a universal thing. It doesn't work everywhere. It only works when you're close to the surface of a planet. Which is great because it helped us a lot when we were doing stuff with just on the surface of the Earth, but we can go further than that. Part of the problem is we don't know this g, the acceleration of gravity for, say, two planets, right? We don't know what the acceleration is that's between those two things. So there's a better way and kind of a more thorough way to calculate that, and that's Newton's universal gravitation. And the equation for it is this. The force of gravity is equal to capital G, which is universal gravitational constant, we'll talk about that in just a minute, times the mass of object 1 times the mass of object 2 divided by the distance between them squared. Now, we use r for distance between them because usually we're talking about, on scales like this, things in orbit. And we're talking about things orbiting each other, that's circular motion, and so the distance between them is the radius of that orbit. Right, so this is distance. Now, this number g, Newton's universal gravitational constant, is the same across the entire universe. So every object, every problem you're going to work, capital G is always going to be the same number. And that number is 6.67 times 10 to the negative 11th. And the units on that are Newton meters per kilogram. All right, that way we get newtons out for our force. And this is an experimentally proved number. This is a proportionality of the force of gravity between any two objects. So for example, if I have planet number 1 over here and planet number 2, I could use this equation to calculate what's the force of gravity between these two objects. Kind of an important idea here is relating to Newton's second law. It's saying, well, how hard does object 1 pull on object 2, and how hard does object 2 pull this way on object 1? In other words, how do these forces of gravity that they exert on each other compare? Well, by Newton's third law, it's pretty simple. If object 1 exerts a force on object 2, then object 2 is going to exert the same force on object 1. So these two forces of gravity are exactly equal. The force that they pull each other with is exactly the same. So we say that this is the force of gravity between the two objects. Okay. One other important note here about r. This distance, is not between the two surfaces of the planet, but is between the two centers of mass. Right? So this is distance between what we call the centers of mass, so like the centers of the planets to where they are. That's a very important point to remember. One interesting application to this, we talked about how we used to use force of gravity equals mg. We can actually use Newton's universal gravitation to calculate this g, the acceleration of gravity, for every planet, as long as we know some basic information about it. The way we do that is that we say, okay, well, Newton's universal gravitation is gravity times mass of object 1, mass of object 2 over r squared. Well, force of gravity is also equal to mg on the surface of a planet, so we set these two things equal to each other. And we say that mg equals g m1 m2 over r squared. Now, we have mass of our object and the acceleration it would experience. Gravity, this would be the radius of the planet, since that's the distance between their centers of mass. So, this mass here is the mass of our object. One of these masses is also the mass of our object. The other is the mass of the planet it's on. So we can cancel out one of those masses. And what that leaves us with is the ability to solve for g depending on the mass of the planet and the radius of the planet. For example, if you were to plug in all the numbers for Earth, right, if you did g, Newton's universal gravitation, times mass of the Earth divided by the radius of the Earth squared, you would get 9.8 meters per second squared. But theoretically, you could do it for any planet now, because now you could do, say, mass of Mars, radius of Mars for Mars, mass of Jupiter, radius of Jupiter for Jupiter. Whatever planet you're looking at, as long as you know the mass of it and its radius, you can figure out what the acceleration is on that planet. With Newton's universal gravitational constant and with what we know about centripetal motion, we can also calculate the orbital speed of an object. So for example, you could calculate, say, how fast a satellite's orbiting the Earth. For that, right, we have our gravity equals g m. And let's go ahead and do satellite and Earth. So mass of the satellite, mass of the Earth over the distance between them squared. And if we have Earth and then the satellite orbiting, there's our distance. Here's our satellite out here. It's orbiting in a circle, so that's circular motion. Well, what keeps it moving in a circle? Force of gravity does. So force of gravity is our centripetal force. So mass of satellite times v squared over r, so there's our centripetal force, equals g, mass of satellite, mass of the Earth, over the distance between them squared. Mass of satellites cancel out, and one of my r's cancels out. So my velocity would be the square root of g times the mass of the Earth over r, and that's how you could calculate the speed at which this thing is orbiting. Now, one very, very important point here, this is a common mistake. This r, remember, is between the centers of mass. So that's from, for this problem, center of Earth to the satellite. Right? So if you had a problem that gave you, 300 kilometers above the surface of the Earth, you'd also have to include the radius of the Earth in that, because it's from the center of the Earth to where the satellite is. So you have to sometimes include the radius of the Earth. So don't let that be a trick. It's always between centers of mass. So I'm going to talk for just a minute about how tides work, because it relates to Newton's universal gravitation. So Fg equals g m1 m2 over r squared. Specifically, it's going to really relate to that r squared part of the equation. So on Earth, the moon causes the tides. We have high tide here, moon, Earth, high tide on the other side, and low tides on the top there. So a little exaggerated picture of Earth here in terms of where the water is on Earth, but it helps us actually visualize what's happening here. Remember that Earth is mostly water, and all that water is kind of connected, so it can kind of all move together, and water has the ability to move and flow. Well, if we look at the distance from here to here versus, say, the distance to the surface of the Earth, kind of below where the water is, underneath the water, you know that this r is less than this r. And according to this equation, if I have a smaller r, that means a greater force of gravity. So I have a greater force of gravity on the surface of the water than I do on the Earth underneath it, so that water actually gets pulled towards the Earth a little bit harder than the surface of the Earth does, and so that causes the water to kind of bulge out like this. Now, maybe the trickier one is, why do we have a high tide on the other side? Well, on the other side of things, let's consider the Earth, and there's its distance there. And then the surface of the water on the other side of the planet is a different r. And this r is closer to the moon than this r, so this r experiences a greater gravitational force than this one, which means the Earth is actually getting pulled away from the water on this side, so it's kind of leaves some extra space there as the Earth gets pulled away. So this sort of combination of different pulls for different distances is what gives us the tides between the Earth and the moon. And it directly relates to this equation because the distance is inversely proportional to the force of gravity it feels. And because r is squared, even little differences in distance can actually make a noticeable effect in terms of the force of gravity they experience.